Welcome to the fourth session on infinite series. Today we are going to prove two of the most important tests, of which are known as root test and ratio test. Okay, well, let us go to do that. In fact, I started the lecture as usual. Something went wrong, so I have to re-record. Okay, yeah. So this is my YouTube channel. You can download the list of videos from here. So it will give the list of all videos. Take for example sequences or infinite series or compact spaces or whatever. It will give differentiation or Riemann integral. It will give all those things in order. Okay, and it will be in the order of preference of learning, and it will be periodically updated and uploaded. So if you subscribe to the channel, whenever I upload the new version, updated version, you will be informed of that. Okay, today's lecture is going to be infinite series, root and ratio test. Okay, reference as in first. So let me skip the few pages because, as I said, I already started something. Let me hope this will work. Okay, so root test, what does it say? All these tests are for positive terms. So let A and B sequence of positive terms. Okay, let us look at summation an, the infinite associated infinite series. So this is the nth root. Okay, you can say ans are positive for any n. Okay, if a is positive for any n, nth root of a exists. Particular an is nth root. For an, you take the nth root of an. Okay, right. So what does it say? The theorem says the following: if there exists r such that 0 less than or less than 1 and a natural number n such that for all n greater than or equal to n, my nth root of an is less than r. Okay, then the series an is convergent. Okay, this is the first version. Second says assume that there is r, okay, greater than or equal to 1, or even just assume that, okay, for infinitely many n, an to the power 1 by n is greater than or equal to 1. Then summation an is divergent. This is the root test. Okay, if I already learned something about root test, do not worry, I'll come to the standard version in a minute. Let me just make sure the recording is going on. Yeah, right. Okay, so let's go. So I have a1 up to an minus 1, and I have an and an for n greater than or equal to n. Right, now I have no idea about this, but remember, for each n greater than or equal to n, I have an to the power 1 by n is less than r. Therefore, if I raise to the power, this will be less than r to the power n. You understand that? Therefore, this will be less than r to the power n, say r to the power capital N, and this will be less than r to the power n. Right? Therefore, the series an, okay, n greater than or equal to 1, okay, let us look at it. K equal to 1 to n minus 1 and plus n greater than or equal to n of an. Right? So this is dominated by summation r to the power n, where n is greater than or equal to n. Right? Each of the an is less than or equal to this. And we know this is a convergent series. Right? Because we know this series is convergent. this series is convergent, so I had omitted only finitely many terms. So for example, up to n minus 1, 0 to n minus 1, keep it 0 0 0 0, right? Then I get this series. Therefore this series is convergent, and this is a finite sum, therefore I know this is convergent. Do you understand the proof? So we are comparing, yeah. So this an or less than or equal to r power n for all n greater than or equal to n. So by comparison test, okay, summation n is convergent. You okay? This is one. We proved one. Do you understand this? Right. Now let's look at the second part. Let us assume for infinitely many n, we have an to the power 1 by n is greater than or equal to 1, right? Then the series an is divergent, that is not convergent. Why? If false, what does it mean? This is convergent. But if it is convergent, what do I know? An must go to 0. The sequence an should be the null sequence. It should converge to 0. But my this implies an is greater than or equal to 1. So it cannot be convergent. You understand that? Yeah, that's it. Proof is over. Okay. Right? Okay. Now let's understand slowly what are the things which happen in this theorem. The first thing you should see is, see, I kept saying when you learn infinite series earlier, you would have been bombarded with dozen tests or more. Okay, that test, this test, and so on and so forth. Okay, and you would have a lot of circus. There will be hundreds of problems like integration. Keep on checking whether this series is convergent, that series is convergent, etc., etc. Which test to use? You have to break your head. But a professional mathematician, as he goes along for higher analysis, he will find he doesn't need any of those things most often. Okay, there could always be exception. Okay, what does he find? He finds the comparison test along with the geometric series is more than enough if he has to deal with series of positive terms. You look at this proof. What did we use? We use comparison test and a geometric series. Okay. Do you see that? That is why, if you remember in the one of the earlier sessions, I said these are the mother of all tests as you most often. Are you following? So pause, review, proceed. Okay, now what is the standard version of root test? It says that let us assume an's are positive, let us assume limit an to the power 1 by n, okay, equal to r. Then it says 1, if r is less than 1, then the series an is convergent, and 2, if r is greater than 1, this is divergent, and 3, if r equal to 1, the series is inconclusive, the test is inconclusive. That is it. You cannot conclude anything definitely. Okay, it's a right. This is the version most of you must have seen. Okay, my thing to makes much easier, but anyway, let us try to understand why this version follows. Now suppose, let us look at the picture. I have r here, I have 1 here, and r is strictly less than 1, right? Therefore if I put 2 epsilon equal to 1 minus r, right, then this is r plus epsilon, call this s, okay, and this is r minus epsilon. Okay, you understand? Right. Now since an to the power 1 by n converges to r, for this epsilon there is a natural number n, so that for all n greater than or equal to an to the power 1 by n lies in this interval r minus epsilon to r plus epsilon, right? In particular, for all n greater than or equal to n, my an to the power 1 by n is less than r plus epsilon, which is s. That is, an is less than r to the power, sorry, s to the power n. What is s? Remember, s is less than 1. So what I have shown? So if the limit an to the power 1 by n exists as r, if r is less than 1, I have shown that there exists an n, a natural number, so that for all n greater than or equal to n, an is less than s power n. Okay, there exists s less than 1 and a natural number n, so that for all n greater than or equal to n, an is. This is exactly, in the earlier case I said r, but I just replaced by s now. That's it. There is no difference. Do you understand that? Therefore, it follows that the series an to the power 1 by n is convergent by my version. We follow that. Next, let's look at the second one. Suppose limit an to the power 1 by n is r, where r is greater than 1. Again, let's look at the picture. I have 1 here, okay, right, and this r is greater than 1, right? Therefore this is my r, right? Therefore r minus 1, I can write it as 2 epsilon. Therefore I can take this r minus epsilon to r plus epsilon, right? Therefore r minus epsilon is also greater than 1. Do you follow that? Yes, right. Now since limit an 1 to the power, therefore for this epsilon there is a natural number n, so that for all n greater than or equal to n, my an 1 to the power n lies in the interval r minus epsilon to r plus epsilon. In particular, an to the 1 by n, okay, is greater than r minus epsilon, call it t. Notice that this t is greater than 1. Therefore what do I have? An to the power 1 by n, yeah, an is greater than t to the power n, where t to the power n is greater than 1. Since t is greater than 1, t power n. Okay, so are you following? Yeah, but my version is better. What did it want? It said for infinitely many n something happens. Yeah, so this is not for all n, for infinitely many n, because if the limit, if the series an is convergent, the limit an should converge to 0, but you are saying for infinitely many n, an is greater than or equal to 1. Okay, that is a contradiction. So that is a much better result. Okay, my version is a better result and easy also. Are you following? Okay, pause, review, proceed. And there is a more advanced version. Okay, this is meant to intimidate a beginner. See, I know from my experience many beginners in analysis have problem with the limsup and liminif, limit superior, limit inferior. Okay, in fact I even know many teachers have problem, right? So now the theorem says the following. Okay, this version says, okay, see what did we do? So again ans are positive, but we don't want the limit exists, but since this is a thing, limsup will exist, right, as an extended real number. Okay, suppose this is less than 1, then the series is convergent. And 2, if lim an to the power 1 by n is greater than 1, then the series is divergent. Okay, now I hope at some time you will make an effort to learn these things. Please look at my videos of limsup-liminif. Within 2 lectures you will be very confident of those things. Okay, please go and watch my videos. So the key to this advanced version follows from facts about some properties of limsup and liminif. Okay, once you see that, you will see why my version, okay, implies even this advanced version. In fact, my version is better. Yeah, just let's quickly say that. So if okay, alpha is limsup of an, okay, then for every epsilon greater than 0 there exists n, so that an is less than alpha plus epsilon. So this is alpha plus epsilon. So all my an's will be here. Okay. Oh, right. Now let's go back to my version. So what do I have? An to the power 1 by a, an's are positive, an to the power n by n. Suppose limsup an to the power 1 by n is r, okay, is r, let us say less than 1. Okay, so I have alpha, I have 1. Therefore I can find an r, okay, whereas if you put 1 minus alpha equal to 2, 1 minus alpha equal to 2 epsilon, this will be alpha plus epsilon, right? Therefore what do I have? So from this it follows that there exists n, so that for all n greater than or equal to n, okay, my an to the power 1 by n is less than r, that is an is less than r to the power n. Okay, therefore the series summation in n is convergent. So the limsup version follows. Okay, next one. Okay, the next version is the following. Suppose let liminf an to the power 1 by n is beta is greater than 1. So I have 1 and beta. So as usual you can find an r which is still greater than 1. Okay, so what is the fact about liminf? It's exactly dual to that. If beta is a liminf of an's, okay, an is some bounded sequence of real numbers, then for given any epsilon positive there exists an n, so that, so I have a beta beta minus epsilon and beta plus epsilon. Okay, for all n greater than or equal to n, my an is greater than alpha minus epsilon. Okay, this is the fact. Now how do I use this fact? Okay, yeah, so let's go back. So lim in an to the power 1 by n is r which is greater than 1. Okay, now again this is 1, this is r, right? Therefore there is a beta which is still greater than 1. Okay, therefore there exists, okay, n, so that all n to the power 1 by n is greater than beta. This is your something like r minus epsilon, right? That means an is greater than beta to the power n. Since beta is greater than 1, beta to the power n is greater than 1, therefore limit an is not 0. That implies summation an is not convergent. Okay, so you can see my results are more powerful. Pause, review, proceed. Now let's look at a ratio test. Again it is the same thing. An's are positive, so let me assume there exists n, a natural number, so that for all n greater than or equal to n, okay, an plus 1 by an, this ratio, okay, is greater than, is less than 1. Okay, is less than r, where r is less than 1. Sorry, right? Then summation an is convergent. The proof is again easy. What do you look at? Look at a1, an minus 1. Now let's look at an, right? For all n, therefore an plus 1 by an is less than r. That means an plus 1 is less than r, yet an times r. Yeah. And an plus 2 by an plus 1 is less than r. Therefore an plus 2 is less than an plus 1 times r. But an plus 1 is less than an times r into r. Therefore an r squared. Therefore an plus k, you know, is less than an into r to the power k, right? Therefore let us look at the series a1 plus an minus 1 plus an plus an plus k, etc. So this will be dominated by, this will be this is equal to a1, this is equal to an minus 1, this is equal to an, but after that this is an into r plus an into r to the power k, etc. Yeah. So what do I get? So I get, okay, the series is dominated by the following series: ak, k equal to 1 to n. The series n, okay, is compared with this series plus an summation r to the power k, k equal to 1, k is greater than or equal to 1. Okay, since r is less than 1, r is beta, whatever. Okay, so this is convergent. Afterwards this finite sum, right? And each of the an is less than or equal to ak, or an is less than or equal to a capital N times r power k, right? So therefore this is convergent series. This means summation an is convergent. So pay attention, in both the proofs what did we do? We took a series of positive terms which are the an satisfies certain conditions. Then what did we do finally? We use comparison. Okay, well, what did we compare with? We compared with a geometric series. This is the trick. That is why in the earlier, one of the earlier sessions, I said the geometric series and comparison test are the mother of all tests, except internal tests, etc. But most of the standard tests which you use for absolute convergence or convergence of positive terms. Okay, right. So now, okay, so there is also a lim version, but suppose what happens if n plus 1, or rather for all n greater than or equal to n, an plus 1 by an is, okay, greater than r, this r is greater than 1. Okay, this would mean, okay, an plus 1 is, okay, an will be greater than an into something, but remember this is, I can do all this is enough for me, and this is positive. Therefore limit an is not 0. Therefore the series an is not convergent. Do you understand this? Do you want me to spell it out? Okay, this means an plus 1 by an is greater than r. Therefore an plus 1 is greater than r times an. Remember r is greater than 1, therefore it's greater than an. And similarly an plus 2 is greater than r times an plus 1, that is an plus 1, that is greater than an, and so on. Okay, that's it. So again this test is usually used using limits an plus 1 by an equal to r. If r is less than 1, then the series is convergent, R is greater than 1, divergent, R equal to 1, inconclusive. For inconclusive, the same example 1 by n and 1 by n squared. So this you can do. And here this is very easy, exactly the same. Remember, see, if this is the one, that means if, right, R is less than 1, okay, or this one, choose an S, okay, where S equal to R plus epsilon, where 2 epsilon is 1 minus R. Exactly the same, right? Therefore, there is n, so that for all n greater than or equal to n plus 1 by an lies in the interval R to 1, whatever, okay, R to R. Are you following? Yeah, so it has to lie in R minus epsilon to R minus epsilon to R plus epsilon. In particular, an plus 1 by an is, what is my assumption? Yeah, therefore an is less than R plus epsilon, which is S. That is an plus 1 is less than S times an. For all n greater than or equal to n, this happens. So this brings you back to my version. Similarly, the second, so I don't want to do anything more, that's okay. There is a next thing one usually sees in infinite series, something like summation an. Now an's are any real numbers or complex number. Assume this is convergent and let epsilon be given, then there exists an n in n that n plus 1 to infinity. This is the way they usually write. This is same as saying k greater than or equal to n plus 1 of ak, take its modulus, this is less than epsilon. Okay, a very naive proof of this will be like this. Let S equal be the sum an, right? Now what is Sn? Sn is a1 plus an, right? Now given epsilon greater than 0, there exists n, so that mod S minus Sn is less than epsilon. Now therefore this means ak k greater than equal to 1 minus ak k greater than equal to n plus 1 is less than epsilon. Therefore ak n plus 1 onwards is less than epsilon. This is a very naive proof. Many people will like this and they think that's enough, but that's not correct, because as I said, you cannot work with that. So first, when I write this a k greater than equal to n plus 1, I want to understand, okay, the meaning. I want to think of this as a number or real number or complex number, right? But this is an infinite, again this is an infinite series, therefore I have to give a meaning to this, right? So what we do is you write, okay, b1 equal to a1 and, okay, maybe b n plus 1, bk equal to an plus k, right? Now let's look at this series, infinite series k equal to 1 to infinity if you want. Okay, now let Tn be the partial sums. Okay, now what is b? So my tk is going to be an plus 1 plus an plus k, right? But what I could do, therefore tk equal to an plus 1 plus an plus k, therefore this I can write as a1 up to an plus k, call this is the partial sum Sn plus k minus a1 up to an, and this is the partial sum of the series Sn. You understand that? Now as what is the limit of tk? K goes to this, so this is the limit of k of Sn plus k minus, this is a finite sum Sn, but this is S. right? You understand that? But limit this is so, but okay, but what is limit tk? Limit tk is nothing other than the sum of the series tk, but this is nothing other than sum of the series an plus k, but this is sum of the series k greater than equal to n plus 1 of a. Okay, you understand that? Therefore what I have shown is summation k greater than equal to n plus 1 of ak is less than epsilon. This is what is called a tail. So if I have a convergent series, give me any epsilon, okay, I can take away the first finite number of terms, then the tail of the series is an infinite series. Its sum in absolute value will be less than epsilon. That is the correct way to understand. Whereas if you try to do it the earlier way, okay, what you get is some algebraic manipulation. So please understand the last proof. Many teachers and textbooks will write s minus sn is less than epsilon, therefore summation, okay, an plus 1 plus an plus 2 plus an plus k modulus is less than epsilon. But you have to say this is an infinite series whose sum is s minus sn, and that we know is less than epsilon. Oh, these are subtle things. Okay, you may find it little difficult. Please review, okay, discuss with your friends, then you will appreciate. We will meet again.